Now, there's actually a certain amount of energy, or a certain fraction of energy, that the EG is destabilized and the T2G is stabilized. So if we say this entire distance between the T2G or the entire energy between the T2G and EG is delta naught, the EG is destabilized by 3/5 of delta naught. So that's the energy increase associated with the EG orbitals. So the EG orbitals are 3/5 times the crystal field stabilization energy. So they're going to be 3/5 times delta naught above the barycenter, which, remember, the barycenter is where is the energy associated with the 5d orbitals surrounded by a spherical field of electrons from the ligands. Now, if this was called DQ, 10DQ, if this was called 10DQ, 10 times 3/5 is 6. So, in terms of DQ, the EG orbitals are destabilized by 6 DQ. Now, the T2G orbitals are stabilized by 2/5 times delta naught. And in terms of DQ, the T2G orbitals are stabilized by 4 DQ. DQ and delta naught tell you the exact same thing. It's just different books do it different ways. Our textbook, if I remember correctly, does delta naught. So, the increase in energy associated with EG is equal to the energy decrease associated with T2G. So, if you look at this, for the two orbitals that increase in energy, if you multiply that by 3/5 delta naught, that will equal the energy decrease of the 3 T2G orbitals, 3 times 2/5 times delta naught. Or, so basically, the number of orbitals times this splitting energy should be equal on both sides of the barycenter. You can also do this with DQ, since there's 3 T2G orbitals that are stabilized. 3 times 4 is 12 DQ. On the other side, since there's 2 orbitals that are destabilized by the ligand field, 2 times 6 is 12 as well. So the energy needed to stabilize the T2G orbitals should be equal to the energy needed to destabilize the EG orbitals. Now, the final energy from the splitting of the d orbitals is actually much lower than the energy of the unbonded d subshell because of the attraction between the metal cation and the electrons on the ligand. Remember, all this was derived from the repulsive effects of the electrons on the ligand interacting with the electrons on the metal cation. However, since there's an attractive force between the positive cation and the electrons, the overall energy of the d orbitals in an octahedral field should be lower than the original d subshell. The most important thing to take away from this is that for any metal cation surrounded by 6 ligands, you will get this characteristic splitting of the dz squared and dx squared minus y squared higher in energy than the original d orbitals, and the dxz, dyz, and dxy lower in energy than the original orbitals. Now, we can take and distort the octahedra as well. So there's some electronic effects that will cause an elongation along various axes. So remember, this is going to be the z-axis, this is going to be the x-axis, and this will be actually, this is the z, this is the x, and this is the y. Okay? So now I'm going to just elongate it along the z-axis. And what happens? That's what happens. You have less interaction between the two ligands along the z-axis and the same amount of interaction along the x and y axes. So, what orbitals are affected by this elongation? Well, you would expect if there's an elongation along the z-axis, the dz squared should be affected. How does this affect the crystal's field splitting of the d orbitals? Well, you might expect that the dz squared and dx squared minus y squared are now going to go away from being equal in energy to different in energy. And since there's less interaction between the ligand along the z-axis and the metal cation, you might expect that the energy for the dz squared orbital should go down. And that's what it does. So let's take a look at this for just a moment. What happens is there is a decrease in energy for the dz squared orbital since the cation is interacting less with the dz squared orbital, or the ligand is interacting less with the ligands. The two ligands are interacting less with the dz squared orbital. And it looks like, according to this diagram, and it's true, that the four ligands along the x and y axes interact stronger, which increases the energy for the dx squared minus y squared. Now, also, for any ligand or for any orbital that has a z component, okay, any orbital that has a z component, it also goes down in energy. And it's because there is less interaction along the z-axis in general. So the dxz, dyz is lowered in energy from the T2G set, and the dxy is increased in energy because, once again, along the x and y axes, those four ligands are coming in tighter. There is a name for this electronic effect called the Jahn-Teller theorem, and it simply states that any nonlinear molecule in a degenerate electronic state is unstable and will undergo a distortion to form a system with a lower symmetry and lower energy, removing the degeneracy. And that's what you see here. You can have elongation along the z-axis, and that will remove the degeneracy between any orbitals having a z component and the orbitals having only x, y components. Now, the Jahn-Teller distortion can occur in two ways. You can have, most commonly, elongation of the two axial bonds, or you could have elongation of the four equatorial bonds. Jahn-Teller distortions are observed in coordination compounds with two types of d electron counts. Okay, keep this in mind. This is important to know. Okay, both of these things are important to know. Certain types of D4 cations, if it has a D4 electron count, that's going to tip you off that you should have a Jahn-Teller distortion. Or D9 cations like copper 2+.